Very good morning to all. Morning. I'm Terence, and I work for Rolls-Royce, and I lead a global Rolls-Royce team to develop and translate exciting new AI technologies across the company. Now, earlier on, I spoke to Atu from DDN, and he was telling me that a lot of the attendees today are not from the industrial technology companies, and that worried him and me to a certain extent. And I was thinking about how should my message relate to you. And I'm sure you'll be wondering what I'm going to say as well. Now, you should be concerned about what I'm going to say because I believe a lot of you fly when you're on business and leisure. When you are overseas, you take commercial trains and ferries. And when you're in offices, you consume energy that you do not know who supplies. Right? Now, all these services can potentially be powered by Rolls-Royce technologies. So I'm sure that you'll be interested to know how we are going to use AI to give you efficient, reliable technologies and services. Right? So this is what I'm going to do. You will hear a lot about AI being used in the context of other more glamorous industry. But what I'm going to do is to give you an appreciation of how AI is going to be exploited and how there are many exciting opportunities for AI in the industrial technology space. So I will set a context for our business, talk about some of the key drivers shaping our business strategy, and then speak a bit about how we have been using AI so far to address some of the challenges. But I will take a step further to tell you about some of the new paradigms that I'm trying to push within the company to bring the company to the next level, and hopefully to use AI to drastically transform the way we do engineering and technology. All right, so let's get started. Now, Rolls-Royce is in the business of pioneering the power that matters. We have products that connect people, products that power the energy that is used in a lot of industries, and we also protect the society through some of our defense technologies. Right, we have three broad business sectors. Our gas turbine engines power many aircrafts in civil aerospace as well as in defense. On land, our products power heavy machineries, trains, and infrastructure. And even out at sea, we have technologies that are used in commercial ferries as well as submarines. Now, sorry to disappoint some of you who might still be thinking that we are still in the business of creating and manufacturing the Rolls-Royce car. We actually sold that business quite a number of years back. All right? Now, what drives our business? You will see that power is changing. The demand from the industries is on the rise, but also changing in terms of the shape and form. Now, if you look at some of the market forecasts, you'll see that over the next 20 years or so, there will be a tremendous amount of new aircrafts that are needed in order to serve increasingly affluent society. This competition, together with increased customer expectation, pushes us to continue to innovate so that we can bring more efficient products and good quality services to our customers. The other aspect that we need to be concerned about is global decarbonization strategy. And that really nudged us to accelerate our product development, to develop new hybrid electric and fully electric technologies, as well as nuclear options. Right? And then you will see that there is a lot of things that we need to do differently. The way we design, the way we make, operate, and maintain the new products will differ very differently from our traditional gas turbine engine-powered solutions. Right? So we need a lot of technologies to help us to be competitive. And we believe that digital capabilities such as IoT, data analytics, and artificial intelligence can help us to address some of these challenges. Data and insight have become more important and crucial in not just driving innovation, but accelerating innovation, and also helping us to make quick quality decisions so that we can stay competitive. Now, let's look at the nature of our businesses within Rolls-Royce and how AI has been used so far. Now, for those of you who are in this space of industrial technology, this is a very typical product life cycle that you will see. The journey starts with having good quality design. Right? We have used machine learning and a lot of computational optimization techniques to improve the way we design the engine, to improve a lot of the design tasks that we need to do, as well as to use machine learning to learn from past design and operations so that we can advance the design of a new engine. Right? And there is a lot of concern about competition because the world is moving very quickly. So we also use natural language processing techniques to scan all the publicly available information so that we can appreciate and understand the intellectual property and competition landscape. Now, once we zoom down to a good candidate design, we develop the physical prototype and put it through a lot of tests. And data analytics is used to analyze the test data and to assess the performance with respect to the new design parameters. Opportunities abound when we talk about manufacturing. We have already used machine learning techniques and various optimization capabilities to improve the way we do manufacturing. Interactive visualization dashboard now ingests data from many different manufacturing systems to give alerts to production manager in an automated fashion. There's a lot of things that has been already automated in the manufacturing process. Now, we use a lot of robotics in our company to do the manufacturing tasks. The problem with robotics is that it requires a lot of experimentation, expensive and lengthy one, in order to set the right process parameters. We now leverage AI to be able to predict those process parameters and therefore skip this lengthy experimentation. And of course, things don't sometimes get right the first time. So when there are problems, we use descriptive analytics and feature engineering to pinpoint the root cause so that we can address the problem. Now, why is that important? Any delay in getting an engine out of the factory causes us hundreds of thousands of dollars in rework and also in delayed delivery penalty. So the more we can do to get the engines out as quickly as possible, the more we can save. Well, quality is important because it affects the safety of our passengers and crew. To do that, we use computer vision and image analytics to automatically inspect the engine and the components, to detect defects and identify them so that we can control any quality escape. And then we move on to the next stage of the product life cycle, in services, where our engines are in operation. For those who are unaware, our business model is based on power by the hour. It means that we only start making profit when our engines are in the air. When our engines are grounded because of technical issues, we pay penalty. So you can probably appreciate why we're using machine learning to do quick, effective diagnostic and prognostic. And the more we can do to put the engines in good shape while it's on the wing, the more time and penalty we can save. Right? And we are also going into new business model as well, trying to provide data-oriented services to the airline companies. So this involves translating data into insight that talks about the efficiency of the airline operations as well as pilot performance. MRO is last but not least. There we use a lot of historical data, repair records, and invoices to give us a very holistic view of the behavior, the life cycle behavior and cost of our components. And that insight helps us to scope our repair strategy. If we are going to set up a new repair shop, where should we have it? What kind of components should we focus on? So this insight helps us to better tune our business strategy. Automated inspection is done here again because we want to determine whether it's safe for us to put the engine back onto the wing. So the inspection will help us detect defects and to replace the components when necessary. What I'll do next is to talk about, well, let me go back here a bit. Those activities that I spoke about are at different levels of maturities, but I hope it gives you a sense of where and what we are trying to do with respect to AI. Now, the next segment of my talk, I will briefly speak about 3 paradigm shifts that we are trying to explore to drastically transform the way we do engineering and technology. Now, let's look at design. We have done a tremendous job going from the old ways of doing physical experiments that are very costly and time-consuming to computer-based, physics-based modeling and simulation. But even then, that modeling and simulation is still very expensive. Right? Because in order to design an engine right, an engine subsystem simulation can easily take weeks to simulate on thousands of processors. Right? And that is not scalable if we have a lot of design options to consider. And then we use AI to improve a lot of these simulation tasks as we go along. And as we get smarter in collecting past engine data and operational data, we also train the computers to learn from this data. Right? For example, in the plot up there, it can tell you what is the variation of the design parameters and how that will affect the performance attributes of the engine. The transfer learning technique that we use also allows us to say, how can we learn from the past design, the problems that we had, and use that insight to advise a new engine design. So if we are given a new engine parameters, we can actually use transfer learning to predict the performance of the new design. Conversely, if you had targeted performance requirement by the customer, like fuel consumption efficiency, we can also pump that into the model, and it can recommend very good candidate design points for you to start your design exploration. Now, where do we go from here? And what kind of challenges can we foresee? Let me use a very simple example. Early this year, a furniture company has used AI to help them design new chairs. All right, chairs that are sturdy and use less material. Now, you'll probably agree with me that for chairs, it's probably easy to make a decision whether you want to make the chair and to buy the chair. For engines, it's a different story. We are talking about safety-critical products that involve more than 10,000 parts with complex interactions. Right? It's not easy for a design chief or the aviation regulators to just accept black box recommended design. Would you? Right? So what do? The key element here is that we need the element of confidence and trust that the design will perform predictably and safely. So we have an idea. If we cannot take the engineers away from the physics, right, we will bring AI to the physics. Now, what do I mean by that? In a recent effort, we have actually used machine learning, neural network particularly, to try to predict the physical attributes of an operating engine. For example, the air velocity, the temperature, and the pressure. Now, what we do in addition to that is, for the neural network, we introduce what we call a particular physics model into the loss function. Now, without going into much technical details, basically, we are trying to avoid having to solve all these complex physics equations numerically, because that takes a lot of time. So what we did is to try to predict the error in the computation. Now, there's a trick to it, because we don't have to solve the equation in order to be able to predict the error. There is the auto-differentiation function that's available in many machine learning tools that we could use. So by incorporating the physics into the loss function that's used to train the neural network, the engineers are more at peace to accept the way we are doing machine learning, because the physics that they understand are incorporated into the machine learning. All right? So where we don't have the physics model, we then rely back on data-driven approach by looking at the past data that we have. Now, we have successfully applied this concept to 2 aspects of our work: the design of an engine subsystem, as well as the design of a hybrid power system. The beauty of it is that it requires less data to train, but there's tremendous saving in terms of time. We we are able to see about 20x to 50x improvement in the design turnaround time when we use this technique. Now let's move on to the second paradigm that I'm going to talk about. I'm not sure about you, but I have a lot of trouble recruiting sufficient and good data scientists, and also to retain them. May I have a show of hands, how many of you have the same problems? All right, it seems that we have some consensus here. Now the question is, do we need data scientists? All right? But to be less provocative, maybe we can ask a different question. How can we be less dependent on them? Now, why is that important? If you look at Rolls-Royce, this is the ratio of data engineers, scientists, to the number of technicians and engineers we have on the ground who are doing the hard work. Now, we cannot afford to have the technicians and engineers waiting for the availability of a data scientist to give them insight, because a lot of time they need to solve the problem right now. All right? So what can we do about that? So we came up with the idea and explored putting together what we call a smart discovery tool to empower the subject matter experts. Now the idea here is no coding, no data science training. What we are trying to do is to embed as much data science knowledge and best practices that we have learned over the years into the tool. Right? And it's important to note that the moment we put a lot of tools together, there will be challenges. So here we use a lot of open source technologies like scikit-learn, SK Feature, H2O AutoML, Delex, just to name a few. And it's not as simple as just wrapping a UI around these tools and then throw it at the users. Right? They will throw it back at you and say, bye-bye, I'll see you next time. Right? So through a lot of agile iterations, we managed to get the tool to a form that can empower the engineers. We give them flexibility to probe the data, to look at the good and the problematic engines that we have during manufacturing. We allow them to zoom into a subset of the data if they are concerned about only a subset of the engines. And they can take a step back to look at all the raw, for example, vibration data behind those data points. And when they're happy with what they have, they can use the tool to automatically generate the key features that represents the behavior of the data there. And they use the tool to help them visually appreciate for a particular feature how it can help to differentiate between the good and the problematic engines. Now, aside from having the insight to know what is wrong, with the manufacturing, the engineers also want models and tools that can help them to predict for an engine that is still being assembled, what is the probability of it having to go through a rework? Because the earlier they can understand and predict that probability, the earlier they can fix the problem and reduce the penalty cost. So they require models that are interpretable, such as the surrogate decision tree here, where the pathway to the decisions can be clearly studied and analyzed. Now, I purposely blurred this decision tree because it contains some of the sensitive manufacturing data that I have. Right? Now, engineers are very action-oriented people. They want to take actions to resolve the problem. But to help them do that, they need to understand how is a particular feature affecting the prediction outcome. So we use tools like Delex to give them this kind of plot. It's basically the PDP and ICE plots, where you see on the x-axis the different values of a feature, and on the y-axis it talks about the probability of coming out with a good or bad engine. Now, when we give this tool to the engineers, they say they couldn't understand it. So we have to go and improve the way we present the data to them. We clearly color code the good engines and the bad engines. Right? And we also recomputed the respective PDP values for the different engine class. And with this annotation, it's now clearer to the engineers that if they are to control the manufacturing process, to keep this feature in the value zone circuit there, they will be able to reduce the probability of having a rework in the engine. Right. Now, many cases, you don't have just one key feature, that tells you the problem. There might be multiple of them. Now, the engineers are very pragmatic people. They cannot afford to look at 10 problems, right? So they need to understand what are the key contributions to the engine problem. So we use plots like this, the sharp-lived values, to help them appreciate the relative contribution of the features to the problem that they have. And by giving them this relative ranking, they can make decisions to prioritize what they should work on first. Right? I'll talk about the last paradigm. In an engineered product company, a lot of the technical knowledge is embedded in the brains of only a few specialists. And the decisions are typically made manually, although now with the support of data analytics and machine learning. Whenever there is an issue with the engine, there could be multiple hypotheses, and it takes time to investigate each one of them. All right? So the challenge is, how do we enable them to do a more effective decision-making? Right? So we came up with an idea, and this is still a very new idea that we are exploring. We have the vision of a digital service engineer in the hope that this engineer can help human experts during the decision-making process. In our vision, this digital engineer can actually observe a wide variety of data about the behavior and performance of our engine. He is able to understand the physics concepts and all the decisions and actions that the engineers took. Is able to reason the what, why, and how of those decisions, is able to establish causal relationship between decisions, events, and the outcome of those decisions. Right? And more importantly, it tries to codify that knowledge and make it searchable. But what is more important going forward is the ability to reason about new observation. Right? New observation, to explore different options that are available to them, simulate very complex scenarios to understand the trade-off, and then recommend optimal decisions. And we hope that this engineer will learn through the feedback of domain experts so that it gets smarter, and then it can share back the knowledge with other engineers, and also to customize training for new staff as well. Now, we think that this is a very powerful vision. Of course, a lot of technological building blocks are needed to realize this dream. But we believe that this vision will help us to drastically transform the way we do engineering. Because currently it's still very manual. There's still a lot of knowledge that we cannot tease out from the engineers themselves. So in summary, this is the takeaway for you. I hope that through this short sharing, you get an appreciation of the exciting AI opportunities in an industrial technology company such as Rolls-Royce. I shared with you the 3 new paradigms that we are pushing to bring the company to the next level of doing very exciting engineering work and producing great technology. But we need to be mindful that we have to deliver AI in a way that integrates naturally with and augment the engineering approach. You don't get things right the first time, so the ability to be agile, to experiment, and to adjust is very crucial for our success. So with that, I wish you an exciting AI journey ahead. Thank you.